So this is the second in a series of 4. Let me try what. So that what I was what I did last time before we stopped was this very simple example. This is the CPU version of this little program. So what this program does, I recall you, is that it has two arrays of numbers filled with random data, and then it applies to these two arrays a certain function of two variables that return 1, replaces the first array, and repeats that 256 times. And these are large arrays with 256 million numbers. Then. And this is the GPU version of the same program. The function that does this computation on the elements of the arrays is exactly the same as before, except that it has this little annotation in front, which is device, which tells the compiler to produce a binary function that will run on the device, and that will be called from the device also. And then there is this other second function, apply function. So this is a special type of function in CUDA that is used, it's called a kernel, and it's used to map a certain operation to the array, to the entries of an array typically, in parallel. So this function is called by a large number of threads, and it will apply this function f to every element of the array in parallel. And then the other steps in a typical GPU computation is that you need to dig. So if you produce the data you're going to operate on the host, then you first need to copy it on the GPU before you can do anything with it on the GPU. So for this, you first allocate space for this data on the GPU. You copy the data from the host to the GPU. This is done in these two lines here. And you have to specify in which direction the copy is happening. So here is host to device. And then you call this function here, which will apply the function f to the arrays. And so I will explain the syntax of this today. And then you need one last copy in the other direction to retrieve the result on the host in general, or other processing, for instance. So I explained the details of this. What I want to show now is what you will change if you wanted to spread this computation on two different GPUs. So this is a case of a computation where every entry of the arrays is processed independently of the other entries of the array. So it's trivially, there is a trivial way to split this computation on two GPUs. You have the first half of the array processed by one GPU and the second half of the array processed by the second GPU. So what changes is that first of all, you have this function CUDA set device with a number 0 or 1. So this is a function that sets what is the active device for all subsequent CUDA operations until you change it again. So for instance, and the devices are numbered from 0 to the number of GPUs you have minus 1. Okay. So, for instance, you do CUDA set device to select the first GPU, and it means that the two CUDA mallocs that follow, they will allocate space on this device numbered 0. Then you change the GPU, CUDA set device 1, and the next two mallocs will allocate space on the first, so on the second GPU, and you see that now I'm allocating only half of the space I was using before, because these arrays will be used to store half of the arrays. And of course, you need different pointer names for the two GPUs. Then you change again the GPU, you do CUDA memcopy of the first half of the arrays onto the first GPU. You change device to the second GPU, you copy the second half of the arrays on the arrays you've created on the second GPU. And then comes the computation itself. So you change to device 0. And you see what has changed here is that you're calling this kernel, but only with half the number of threads you were using before. And the same is here, but now with the pointers that live on the second GPU. And then you change device again to retrieve the partial results from each GPU. And one thing to note here is, so the CUDA memcopy function is a blocking function. So what this means is that it returns to the host only after the copy has been finished. This is a kind of safety measure, if you want. It means that you will not be tempted to change the source array before it has been completely copied to the GPU. Because if it were returning immediately and to the host, and then on the host you start modifying this array before it has been finished copying on the GPU, you will get nonsensical results. So these are blocking, but the functions that do the computation, so the CUDA, the kernels, they are not blocking. So it means that even if this operation is taking a long time to process on the first GPU, this call returns to the host immediately, which means that you can start the computation on the second GPU immediately before the first one has finished. And for computations that need a certain amount of time, it means that the computations will happen in parallel on the two GPUs. Yes?
What would be the command to know how many GPUs you have available?
There is one, I'm not sure, I don't know it off the top of my head. There is certainly a command. And so in general, you know that because you know the computer where you're doing the computations. If you really don't know, there is a software way to know this number. And there is also a software way to know the amount of memory available on a given GPU, what is its model, and so on. So here, one thing I didn't say, I think it's on the next slide. Yeah, it's written here. The way these numbers are chosen, 0, 1, and the way they are mapped to the available GPUs is not something you can decide as a user. It's something which is automatically assigned when the computer boots. So in most of the cases, at least for big computing centers that provide computing time, if a computing node has 4 GPUs, they are all of the same brand and model. So you don't care which is the order; they have the same amount of memory on each. If you're on a computer where you have GPUs of different types, and especially GPUs with different amounts of memory, there is indeed a need to know which GPU you're talking to, because otherwise you run the risk of running out of memory on a certain GPU. And this is where you would like to know from the software if the GPU 0 is the one that has 1 or 2 gigabytes. And this is possible, but I've never used these functions. So there are a few things I already said. The important function here when you manipulate GPUs is this function CUDA set device. It allows you to make one GPU active for all the subsequent calls until you change it again. You don't need to change the kernels when you use several GPUs. The same kernel will run on all of them. You may call them with different number of threads on different GPUs. There are cases where the GPUs are different models and they require different compilation flags when you compile. So it's possible to instruct the compiler to produce binary instructions for several GPUs at a time. So this will be encapsulated in the same binary file. And then when it runs on a certain GPU, it will pick a subset of the binary file, another subset for another GPU. Yes, so one thing I said is that the mapping between the GPUs to their index is not something you control. And then in the example of program I flashed here, there is still a little bit of improvement, perhaps, which is that there is an asynchronous version for all these memory operations, memcopy, malloc, and so on. So if you use them, there is a potential to make some of them happen in parallel. And there is a greater risk of doing wrong things with the synchronization, because if those return immediately to the host, and you have to be more careful when using them. I will talk about these functions later today. So this is where I wanted to finish the lecture last time. And now we're going to start, something about the times it takes for this example. So this is a test I did on one of the nodes of this computer at Idris. So on the CPU, which has 20 cores, it takes 25 seconds. With one GPU, it takes, say, 2 seconds. So it's 12 times faster, roughly. One improvement, which I talked about last week, is that this loop, when you repeat the same operation over and over again, you can put this loop inside the kernel so that you save the cost of the kernel calls. Then it goes to 1.2 seconds. And then if you use 2 GPUs, most of the stuff does not change. All the memory allocation and all that doesn't change because I'm using the working functions. But the thing which changes is the processing itself, which goes from 0.30 to 0.15. So it's divided by 2, as you would expect. But because in this example is so trivial that the computation time itself is a small fraction of the total, using 2 GPUs brings you very little, in fact. So this is another thing to keep in mind. It's not always a gain to use more GPUs. It depends on what are the other overheads. Yes?
So in this example, it shows that it has been done sequentially, the computations.
No, the computation, so what I call processing is really the duration of the kernel, so the part that does the actual computation. So it goes from 0.3 seconds to 0.15. So you do gain a factor of 2 by using 2 GPUs instead of 1. But in this example, you see that 0.30 is not a big fraction of the total time spent. So if you reduce by half this part of the work, the impact on the overall time it takes is not so great. So having using several GPUs is something which is more beneficial if the ratio of computations to all other overheads is larger than in this example.
So it seems that copying is what taking all the time, right?
In this example, yes, because I'm copying rather large arrays. Let me show the example again. The arrays have a size of 256 million entries. Each of them is a float, so it's 4 bytes. So the arrays are 1 gigabyte each. So yeah, it takes some time to transfer that. It's not super long, but there is definitely an overhead related to that. It's not free. So this is something to keep in mind. It should be avoided to transfer a lot, to have a lot of transfers, especially back and forth of data. A better strategy is to have a data set that you copy once to the GPU at the beginning of your program, and then you do a lot of processing on the GPU, and then at the very end you retrieve some result to the host. If you copy to the GPU, you do some processing, you retrieve the result for some further processing on the host, you send it back. This is not so good. But it's really the same mindset as when we do computations on the CPU. You want to minimize the access to the memory and have your algorithm work mostly from the cache if you can. Yes?
The example you've shown, what's the amount of capacity you use of the GPU, 100% or?
No, so when I run this on my laptop, it's a sizable fraction because the GPU on my laptop has 4 gigabytes. And I guess here these arrays are 1 gigabyte each. So I'm using half of the memory of the GPU. When I run this example on one of the nodes at Idris, the GPUs have 32 gigabytes each, so I'm using actually a small fraction of the available memory. I don't think there is a lot of any penalty for using almost all the memory of the GPU. It either works, or if you're using too much, it just fails. It will just crash if you try to allocate more memories than there is available. For instance, something bad will happen. Okay, so yeah, one last slide that I wanted to show last week also is that you can find a lot of documentation online about CUDA. The reference documentation is available on NVIDIA website at this link. It's essentially the reference manual for all the functions that exist in CUDA. It describes in detail all the functions. They are grouped by topics. And it's very useful if you know the name of the function and you want to check the syntax, how to call it, what are the possible outcomes in case of errors, for instance, and so on. Another useful reference, which is more oriented towards examples, is also on NVIDIA website, and it's a kind of blog where each entry discusses a particular topic. So these are not very long discussions. You can read it in 15 minutes typically, and it's accompanied with full examples that you can compile on your computer to play with them. And then, of course, there are plenty more tutorials on the internet. You can find a lot, but the quality of these last resources depends a lot on who wrote it, and there is a non-zero fraction of wrong information, of course. While the documentation written available on NVIDIA website is almost guaranteed to be correct, and written by people who know the software well because they invented it. Okay, so this is the official beginning of the second lecture. What I want to discuss during this second lecture are these 3 topics in pink. The first part is to give you a few hints about what you can do if you wrote a CUDA program and, well, it doesn't work. Okay. There are, of course, many reasons why it could not work. It's a rather common situation. And so I will show you a few things I use to try to discover where the problem is. The second part I want to discuss is in more detail all the memory management functions, how to allocate memory, copy memory, initialize memory, and so on. And then I will go in a little more depth into the syntax of CUDA kernel, so the special functions that are used to do parallel computations. So let me start by how to try and discover errors. So, by discovering an error, I'm assuming I'm at the stage where the program compiles, because if the program doesn't even compile, it's really a different kind of problems that you have to discover. So the program compiles, but when you run it, it either crashes, which is probably the best case, or it runs but it produces garbage. And this, of course, happens a lot. And the main difficulty with this is that we're talking about a program where, so if the crash you think comes from code that runs on the host, basically you do it as you would usually do for a program that runs on a CPU. But the problem, it comes rather when the mistake happens in code which is running on the GPU. And the main complication with debugging that is that we're talking about functions that will have, I don't know, several thousand threads or even tens of thousands of threads. And it may happen that only one thread is causing the mistake, and the question is, how do you find out where the mistake comes from? So some common causes of problems are very similar to the causes of problems on code running on a CPU. You have a pointer, but you forgot to initialize it, so it's just a pointer without associated memory attached to it. And the first time you try to write or read from it will cause the program to crash. So this happens for the GPU as well. Another common cause of mistake is you're mixing pointers associated to memory on the host and pointers associated to memory on a GPU. So this, of course, if you give to a function which runs on the GPU a pointer that corresponds to memory on the host, most of the time this will not work, and the program will crash. So it's advised to have a naming convention for pointers which clearly indicate just from the name whether it is supposed to be a pointer corresponding to memory on the host or memory on a GPU. It's always a good idea, so that when you look at your program, you know whether this pointer is used in the right context. Of course, common typical mistake is that you've allocated 1,000 entries in an array, and you messed up with the index which is reading into this array, and it goes too far, and you're reading beyond the array, or writing beyond the array. So if you try to read beyond the array, typically you will get either garbage or something that was there before but which is unrelated to your program. And if you try to write beyond your array, sometimes it works because there is nothing important where you try to write, and sometimes you try to write into an area which is where you're not allowed to write, and then the program crashes. So there are several ways to try to figure out these problems. As with ordinary programs, you can try to print the content of some variables. Okay, and you can do that from CUDA as well, from code which is running on the GPU. So the syntax is the same as usual. You can print several variables. There is one problem, which is that if you have a print statement inside a function which is called by 2,000 threads, it will print 2,000 times. So, and of course, the output will be pretty much useless for several reasons, because it's just overwhelming. And also, you have 2,000 threads calling print almost at the same time, but not exactly, and you have no control of the ordering in which these print statements will go. So you get 2,000 lines of output, and unless you're super lucky, they will not be ordered by thread index. It will just be random. So if you have to do this to understand or to inspect the content of some variables in code running in parallel, you most of the time will put a test which is selecting one particular thread to do the print, and all other threads will not print out anything. This will not help if you're trying to find a mistake which happens only in one particular thread, unless you know what thread it is. But for more generic mistakes, it's useful.
Yeah, sorry. I'm just comparing with the OpenMP. There you have instructions. For example, you can decide, oh, this instruction should be executed just by one thread at a time. Is there something similar?
No. So this test is doing that for you.
Yes.
Also in OpenMP, for a print statement, you have an ordered instruction which tells this instruction will be executed in the order of the thread numbers.
Okay.
I don't know of anything similar in CUDA. Yes.
I asked the question because it prepared, and I think I asked the question, but about the the red stuff that is written here, which is the IDs.
Yes.
So it's an int, like 5.
So they are integers. So I will come back to that later today. The threads are organized in blocks, and then within each block they have a thread ID, which is an integer. So all these are integers, and this combination gives you the absolute index of one thread in the full parallel computation. Okay. So you're selecting only the very first thread out of possibly many. But you could have put here it's a 0. You could have put 20 to select the thread number 20. So this is one way to debug code. It's a rather primitive way, but it's very useful. Another thing which is sometimes useful is that you have a program, and in fact it runs, it doesn't crash, but the output is not the numbers you expect, and you get this thing which is called not a number. So it's actually a special encoding of the floating point format, which corresponds to nothing which can represent a genuine number. And this happens, for instance, if you read out of bounds of an array. So either you read garbage which does not even correspond to the valid representation of a floating point number, and you immediately get this thing called not a number, or you get existing numbers but which are gigantic, like 10 to the power 300. And as soon as you do operations on them, you will get something which are not valid numbers. So when you get that in the output, often there is an interest in knowing where in the code they start appearing. So you want to test in some places in some parts of the computation where these things first appear. So CUDA has a function which is called isNone, which takes a float or double precision number as argument, and it returns false, so 0 if it's a valid number, and it returns 1 or 2 if it's not a number. So you can use that to test the content of some variable or array. There is a function with exactly the same name in the standard C library, so you can also use that on the host. Yes?
So So actually, if you have messed up assigning the memory, for example, with the pointers, and you try to read something that does not exist, do you get the NaN error or do you get a compiling error?
No, the compiler doesn't check the bounds of the arrays in C. If you're using a more restricted language like Java, for instance, I think it does, it will do, but in C, no. The compiler will not find, especially at compile time, it will not find these mistakes. Maybe I have to soften a little bit this statement. If you have a statically allocated array, like you allocate something in this way, float A 100, and then you have later on this statement, and note that I put 200 here, and then inside you access A of I in some statement. Maybe in that simple case, the compiler is smart enough to analyze your code and say, hey, you're using an index which is larger than the bound here, and the compiler will tell you. But for anything allocated via malloc, the compiler doesn't keep track of the sizes of the allocation, and it will not detect these errors. In this case, perhaps it does.
So then in that case, in general, we would expect that NaN error.
It depends. So here, perhaps the compiler will even fail to compile your code, so you will not reach that point. But if you read out of bound, the outcome is pretty much random. It could be not a number, it could be some perfectly reasonable number, but which has nothing to do with your computation because it's a remnant of a previous computation. So anything can go. But what is sure is that your program is not doing what it's supposed to do. So in fact, if you get not a number, it's perhaps the best way to spot the mistake. If the worst is that in this area where you're not supposed to read, you have perfectly reasonable numbers, it will take you a lot more time to find that there is a problem. So one thing is that if you want to check for not numbers in a very large array on the GPU, there is a way to do that in parallel as well. You don't have to check sequentially all entries of the array. I will explain how to do this type of things next week. One thing is that I'm not sure about the CUDA compiler, but the GCC for compiling C on the host, if you have these tests for not numbers in your code, but then you compile with GCC with some rather high optimization level, like either O2 or O3, most of the time GCC will remove the test because when you run with optimizations, the compiler assumes that no function can return not a number, and whenever it sees not a number, it says, oh, that cannot happen. So in fact, the test will be useless because the compiler has removed the test. So there is a trick to avoid that, which is to code it yourself. So I found that on the internet. These are ways to actually check for not a number, either in double precision or single precision. And these magic numbers here, they correspond, they will spot the binary representation of not a number, which is uniquely defined. And these functions, the compiler will not remove. So this is something useful. So sometimes you know there are not a numbers in your array, and you do the test, and the test doesn't find them. It's because the compiler has removed them. So now comes another type of thing you may want to find out. Your program crashes because probably something wrong happens in the code running on the GPU. but because many CUDA calls are asynchronous, so they return to the host before they have completed their task, it may happen that the crash happens quite a bit later after the moment where the faulty instruction was issued. So there is a way to check for errors after every CUDA call. So this is a typical way of doing that. It's a kind of macro which will which will check the error after the last CUDA error. It will check more exactly. So you have to include this piece of code at the beginning of the file containing the CUDA functions you want to check. You can either just copy and paste it, or you put it in a separate file, and then you include this file in the header of the file. And then the way it's used is that suppose you have a sequence of CUDA calls and you don't know which one actually produced or made the program to crash. So you can decorate this sequence of CUDA calls by one call to this function, CUDA check errors, after in between every CUDA call, and you put the string you put here is just a tag that will be printed out if the program crashes at this place, and therefore you know which one of these error checks triggered the printout. And that's a way to know, to see if it crashes in this, if the error happens in this call, then it will be, this one will trigger and print this, plus other information about the error. And the execution will not proceed to the later calls. So this way, you can identify, it doesn't tell you very easily what is the mistake, but it will tell you in which function the mistake happened. Except for that, so it's very useful for that. It tells you some information about the line number where the faulty instruction occurred. But the rest of the error messages I find are a little cryptic, but sometimes they are useful, not always. Okay, so are there questions about how to find mistakes? One thing I forgot to say is that the CUDA compiler comes with a CUDA debugger also, which I've never tried, so I don't know exactly how it works, but this exists. To look into it. So now I want to switch to a more in-depth description of all the memory management functions. CUDA provides many functions to allocate, free, set memory, copy memory from the GPU to the host or between two GPUs. The list of these functions with a detailed description is at this place, and you will see there are many more than the ones I'm going to describe. So those I will describe are those that have been useful at least once. For those that I've never used, I will not talk about. So I want to flash this picture. It's a reminder of the memory layout of a GPU. So you have what is called global memory. This is where most of the memory of the GPU sits. And it's called global because it's memory that you can read and write both from the GPU and from the host. So it's seen from both sides. Then you have two levels of cache, L2 and L1. L1 is the one which is the closest to where the computations are done. In fact, it's a part of the same chip as the computing cores. And a peculiarity of the level 1 cache is that a part of it is in fact controllable through your program. So you can say you want to reserve a part of this L1 cache as shared memory that will be used to communicate with the threads. I will show you examples of how to do that. For now, I will be talking about the functions to manipulate global memory. So the first one is CUDA malloc. It's used from the host to reserve some space in the memory of a GPU. So if you have several GPUs, you first have to do a CUDA set device to choose on which GPU you're going to allocate memory. Otherwise, the syntax is pretty much similar to the ordinary malloc. You first declare a pointer, and you give the address of this pointer to this function. And if it returns without errors, the pointer will be filled by the address where this memory is available. Very important thing to keep in mind, but it's the same as with the ordinary malloc. This function gives you a pointer, so it's like the key to enter a safe where you will put your data, but it does not empty the safe. So if this part of memory has been used before by some other process, it's not cleared, it's not full of zeros, for instance, it's filled with whatever was there before, which could be garbage as well. So if you don't initialize this memory after allocating it, probably your program will not work. Another technicality is that, but this you don't have to. In general, the term is storing any kind of data. So if I store an array of double precision numbers, and double precision numbers are 8 bytes, the value of the pointer has to be a multiple of 8. So this function returns pointers which can be used for all command types. You don't have to worry about this. The second argument here is the size of the allocation you want in bytes, and usually you don't give the number in bytes. You need you write how many numbers you want, and you call the times the function size of the type you want. So this way is simpler for not making mistakes. And this function returns errors. So it returns codes to signal certain errors. For instance, if there is not enough memory for the allocation, it is always advised to check for the error. And I must confess, I never do it. And probably I should. It's something useful in certain cases. The counterpart of CUDA malloc is CUDA free. So you give it the value of the pointer that was created by CUDA malloc, and the corresponding area in memory will be freed and returned to the common pool for other processes or future applications. And CUDA free is not clearing the data after you, which means that the next CUDA malloc that will use this data will start from whatever you left. Another thing which is important to keep in mind is that CUDA malloc works only with the pointers created. Sorry, CUDA free works only with the pointers created with CUDA malloc. If you try to call CUDA free on a pointer which is created by the system malloc on the host, this will fail. The CUDA has no knowledge about the memory allocated on the host unless it was allocated by CUDA itself. I will tell you in a while. And then a common mistake is that you call CUDA free several times on the same pointer. After it has been freed once, it's a mistake to call it a second time. This will make the program crash most of it. So second very useful class of functions is CUDA memcopy. So this is a function to copy data from the host to a GPU, from a GPU to the host, or between two GPUs also, if there are several GPUs. The arguments are easy. It's roughly the same syntax as the memcopy that exists in standard C, with one more argument at the end. The first argument is the pointer of the destination. The second argument is the pointer of the source. The size indicates how many bytes you want to copy. And then the last argument indicates the type of transfer you wish. So it can be one of these four things. Host to device, device to host, device to device, and then default. So default, I will tell a bit more about that later. It means you let the program try to guess what you want. And in fact, there are many cases where it can make the good guess just by looking at the pointers. So there is this recent enough GPUs. There is something which is called unified memory, where the pointers have different values depending on which device they correspond to, or also host. So just by looking at the value of the pointer, the program knows that this pointer is backed by memory on the first GPU. And then something I mentioned already is that this function is synchronous with respect to the host. So what that means is that it blocks and returns to the host only when the copy is completed, or at least when it's safe to reuse the array, the source array. So that way you cannot modify the source array before the copy is complete, which is useful. A slightly more complicated version of CUDA memcopy, which is sometimes useful, but the syntax to call it is a bit more complicated. It's for situations where you have an array and you want to copy, for instance, one every 3 elements of this array. And so here it will be like 2 elements every 5. So the purple elements I want to copy, the green elements I don't want to copy. And then in the destination array, I will place these 2 elements with gaps of 2 like this. So it's the typical situation where you want to do that is that you have a matrix, and of course in the memory of the computer, the array that represents the matrix is just one big linear array where the first row of the matrix is the first chunk of this array, the second row of the matrix is the next chunk, and so on. And then you want to copy not the rows, you want to copy the first column of the matrix. And the first column of the matrix means copying one element every, depends on the size of the row. So you could either do it in a loop where you copy, inside the loop you do a copy of 1 byte at a time, no sorry, 1 float at a time, so 4 bytes. But this is rather inefficient because calling CUDA memcopy has a certain overhead. If you want to do it 1000 times for a large matrix, for just 1 float at a time, it's not very efficient. So this is more efficient. It does this copy with stride in just one call. You just need to learn to get familiar with the syntax, but it's not so hard. Okay. So let me finish with this, and then we can go to maybe you can use it. So suppose you have allocated memory on the GPU, and you want to set this memory to some value because it's still an initialized. So for instance, you want to set all the values to 0. This is a very common function. So this can be done with the function CUDA nameset, where you give the address of the pointer, the value you want to initialize it with, and the how many bytes you want to initialize starting on. So the common way of using this function is where the value is 0, so you will just fill all the entries of the array with zeros. And after that, you have sensible content in this array. Just one remark. The type here for value is an integer. It's 4 bytes, 32 bits in single precision, but only 1 byte of this integer is used. So it initializes all the bytes of the array with the same value. So I don't know. I know what happens if you use 0 for the value, because how to say, 0 is like having 4 bytes which are all zeros, so there is no ambiguity. If you use, I don't know, 1, 2, 3, 4 for this value, I don't know exactly which of the bytes in value is used to initialize the array. So you will have to test. And if your goal is really to initialize the array with the full value of this integer, so the 4 bytes, and you repeat these 4 bytes over and over, you need a different function to do that, which is this one. I've never used it, but the way it works is that value now is an integer, and the 4 bytes of this integer are used, and the first 4 bytes of the target array are initialized to these integers, and the next 4 bytes are so and so on. And n is not a number of bytes, it's a number of times you repeat this pattern. I've never encountered a case where I wanted to use this. So this one is much more commonly used, and just with 0. Okay, so I will stop here for the break. I think it's a good time. And next I will discuss the asynchronous version of these functions, so the functions that return immediately rather than blocking.
Maybe there are some questions before we stop for the break in the room or online.
So let's continue. So I have just described all the, not all, but the most useful memory management functions in their synchronous version. So what this means is that when you call one of these functions, it returns to the host after having terminated its task. And then all these functions have also an asynchronous counterpart. The name of the function is very easy. It's the same name, but with async as a suffix. And they take the same arguments plus 1, and the last argument is what is called the stream. The type is this type, CUDA stream _t. And I will explain in a second what a stream is, but what you can think, the way you can think about it is that a stream is a pipeline in which you put a sequence of CUDA tasks to be performed. So on a GPU, there is something called the default stream, and in fact, it corresponds to replacing this variable by just 0. And the default stream is where all the CUDA tasks will be counted. It's a pipeline where all the CUDA tasks will be appended if you use a default stream. You can create your own streams as well with this function CUDA stream create. I will explain how this works next week. And so what this means is that all these functions will be added to the queue of the stream you indicate in the last argument. And if you send 2 of these functions to 2 different streams, they can perfectly be executed in parallel. So What you don't want, of course, is to do an allocation in a stream and do a read of the same memory in another stream because you don't know which one is going first. And if you try to read before it has been allocated, it will not work. But if you allocate a certain array in a given stream and you read a different array in another stream, this can perfectly work. And that way you can parallelize also the memory management operations. But of course, if your intent is to allocate, then set the value, and then read the memory associated to a certain array, you will better put these three operations in sequence in the same stream so that they stay ordered. So the things you queue in a given stream, they stay ordered. The first one you put in the queue is executed first. So if you do that, there is no risk of reading before setting the memory. And the ordering between two different streams is random. You have no control over it. So this I said, a stream is like a pipeline of CUDA instructions. Commands that you send to two distinct streams, I think it doesn't work for the default stream, but non-zero streams can overlap if they don't use the same resources. So for instance, you can also send to different streams computations, not just memory operations, but if a first computation in one stream is already using all the cores available on the GPU, there is no miracle. If you send a second computation to a different stream, it will have to wait until computing cores become available. Yes, this is something I alluded to. If you send subsequent commands using memory in the same stream, and you send them in a logical order, so you set the memory before reading it, there is no risk of using memory which is not yet initialized, because the commands remain sequential within a given stream. But they return to the host before being completed. Yeah, so this is something I've already mentioned. If you try to access memory allocated within one stream from another stream, it's super dangerous, and most of the time it gives undefined behavior because you don't know in which sequence the operations on different streams will be executed. So you very well try to read before initializing the memory. So now another topic I want to talk about regarding the management of the memory is how you can copy from one device, from one GPU to another GPU. So there is first a function you need to call to make that possible, to allow that, because by default it's not allowed. So if you are on the GPU number 0 and you want to read or write to the GPU number 1, you first set the current device to 0, and then you call this function with device ID equal to 1. So this will allow GPU 0 to read or write things on GPU 1. And there is a 0 here, and it's important because otherwise it will not compile, but it serves no purpose. The documentation says this should be 0. It's reserved for later modifications of this function. That's part of the work in progress, I guess. It's still 0. One important thing to keep in mind is that this function gives you a unidirectional permission for one device to access the memory of another device. But if you call this from device 0 with device 1 here in the argument, it doesn't imply that device 1 will be allowed to read from memory of device 0. So you have to call it twice with the roles of the two GPUs swapped so that you can read in the read or write in the two directions. And this is something you do only once during the entire execution of the program. So typically, if you have a program that needs this feature of writing and reading between the different devices, you do that at the beginning, and you're done for the life of the program. So once you've done that, there are functions to actually copy memory between GPUs. They are called CUDA memcopy peer, or there is the asynchronous version of the same function. They take several arguments. One is a destination pointer and the destination device. So you have to specify which pointer you want to write and on which device it's located, this pointer is located, or on which device the memory corresponding to this pointer is located. You have to do the same for the source, so you have the source pointer and the device where it's located and the size you want to copy. And for the asynchronous version, you need one extra argument, which is a stream you want to send this instruction to. One argument you don't need anymore is the type of transfer, the last argument of the normal memcopy functions, because if you're using one of these two functions, it's clear that you want to copy from a device to a device, and therefore you don't need to specify that anymore. And another thing is that it's perfectly allowed for the source device and the destination device to be the same when you call this function. So you don't need to treat as a special case the situation where the two devices are the same. It will work with this function as well. A last topic I want to mention in this discussion about the memory functions is the concept of unified memory. So with what I described so far, every pointer corresponds to data which is located on a given GPU, and it's your responsibility to remember on which GPU you have allocated the memory. But recent devices, in fact, it depends a little bit on first of all, on the GPUs. They have to be recent enough, and on the way they are connected to the host. So even if the GPU supports that, it's not totally obvious that the computer as a whole will have this capability. But there is a software way to check for this capability. It's what is called unified memory. So unified memory means that the values of the pointers are different or in a different range depending on which GPU is holding the memory corresponding to the pointer, and also the address space for memory on the host is also distinct. So just by looking at the value of the pointer, the software knows where the corresponding memory is located. So a first benefit of that is that you can, if your system has this capability, you just use CUDA memcopy default for all your transfers, and the software will figure out where to read and where to write. And if you have a pointer and you want to know from the software where the associated memory is located, you can use this. I've never had to do this, but this possibility exists just by inspecting the value of the pointer. The software can tell you where it is, whether it is on the host, on GPU 0, on GPU 1, and so on. This concept of unified memory extends to the memory of the host, but for that you need to replace the calls to the ordinary malloc you will do in your standard C by CUDA malloc host. So it's a CUDA function to allocate memory on the host. And by using this function rather than the system, the malloc of the underlying system, you let CUDA know about all the applications on the host as well. This way, CUDA will know if a pointer on the host is really on the host. And this way, also, the unified memory has an additional merit, which is that you can call a function that or a kernel that will run on a GPU with a host pointer. You don't even need to copy first the data on the GPU. You just pass it the host pointer, but provided it was allocated with CUDA malloc host, you pass it this pointer, and the data that will be used by the kernel will be copied directly from the host to the GPU as needed. How this works under the hood is not specified in the documentation, so it's not clear if it copies little chunks at a time or big chunks. It's probably optimized in a certain way, but it's not something you can control. But the data from the host will be automatically transferred to the GPU as needed. But you still need to, and also between two GPUs, this works as well, provided you've allowed reading from one GPU to another GPU. There is a subtlety here, which is that if you allocate memory with these two functions, CUDA malloc or CUDA malloc host, the allocation is attached to either the host or the GPU where you created it. But and when it's transferred to another GPU to do a computation, for instance, it doesn't mean that the entire array is transferred to this other GPU. It just means that little chunks of this data are copied as needed by the second GPU. And if you have another kernel which needs again this data, it will have to be transferred again. But there is a possibility to do the allocations with another function called CUDA malloc managed, and this. So I've never used it, so I'm a little bit unfamiliar with this. I understand this function can allocate data on the host, on GPUs as you wish, but the data is not, how to say, is not attached forever to the place where it was initially created. So if at some point the code uses this data from another GPU, it might be transferred in full to this other GPU, and now the second GPU becomes the host for the place that holds this data. And the CUDA keeps track of where this data is. You don't have to worry about that. It's just transparent. The data is somewhere. It could be on the host as well. And I believe it tries to optimize where it puts the data depending on how much space is available and where it's used most of it. But it's something I'm not totally sure whether this function is meant to be something that just simplifies the life of the programmer because it avoids to have to worry about where the data is and to copy it, or it's meant as a way to make the program faster. My impression is that it's more to simplify the programmer's life by just having one huge memory space and the data is somewhere and you don't have to worry about where it is. Okay, so this is the end of what I wanted to do. The memory management functions. Are there some questions before I switch topics? Okay.
So yes,
So when there is such a kind of implicit transfer between data from the host to a GPU, for instance, then you don't have to free it, I guess. When it's transferred to the GPU, you don't have to free it, right?
No, it's the space becomes available on the first GPU. So suppose you allocate this data on GPU 0, and then you run a kernel on GPU 1 that uses this data. This data perhaps will be transferred in full to GPU 1, with freeing the space on GPU 0.
No, but I was not asking about this manage mode. But
In the first mode, probably it's a little irrelevant because my understanding is that this data is transferred little chunks by little chunks, so it will never use a large amount of space on the second GPU. It's not like it will create another array as big as the first one on the second GPU. It will, but I don't know what is the granularity of these chunks. I don't know.
These chunks are deallocated automatically.
Oh yes, yeah. It's more like temporary buffers that are used for these transfers, and they are not large. I mean, a few kilobytes perhaps, or a few megabytes. If you have a 10 gigabyte array on GPU 0, it will not be duplicated integrally on GPU 1. It will compute chunks by chunks. and it's totally transparent for the user. Okay, so now my last topic for today is CUDA kernels. So a kernel is a special type of function that maps in a parallel way a certain action on the entries of an array. Typically, that's what it's used for. A kernel runs on a single GPU. You cannot have a kernel which is split, whose execution is split across various GPUs. But its threads may be distributed across various little chips that are present in the same GPU. There is no guarantee that all the threads will run on the same chip. The threads of a kernel, so you can have many threads. It's recommended, in fact, to have many threads for running a kernel. The software groups them in what is called blocks. The size of a block, so how many threads there are in a block, is something which is chosen by the programmer within certain limits. The upper limit is 1024, so this is a hardware limit because CUDA will run all the threads in a block on the same chip, and probably the upper limit on the number of threads in a block comes from how many computing cores there are on a given chip. And the lower limit is, I think it's not a strict limit in the sense that nothing prevents you from using a lower number. It's 32, and this limit comes from the fact that the smallest number of threads that the GPU will schedule for running is 32. So even if you ask for 2 threads, you will waste the other 30 threads, but it will nevertheless use a chunk of 32 threads. So it doesn't make sense to choose a block size less than 32. Another important property of blocks is that because they run on the same, so these chips are called stream multiprocessors, SM. Because they are on the same of these chips, they see the same L1 cache and also the same shared memory, because the shared memory is a part of the L1 cache. And there are tricks to use a shared memory as a way to exchange data quickly between the threads of the same block. And we will see examples of that later. Another thing which is important is that the threads, there are functions to synchronize the same block, but there is no easy way to synchronize the threads in different blocks, except when the kernel terminates. One of these functions to synchronize the threads in the same block is this function, 2_sync threads with no argument. And this function basically will just block until all threads in the block have reached this point. and then execution will continue afterwards. So now I will have two parts in this discussion. The first part will be the declaration of the CUDA kernel in the code, and then how you call it when you want to run it. So the declaration is really very much like a function in C. You have a name and arguments, and it's preceded by this keyword global, which indicates a CUDA kernel that will run in parallel. And I believe the name global comes from the fact that it's called from the host compute. The arguments of the kernel are like in usual C or C++. They can be scalars, so floating point numbers, integers, structures, pointers. There is a limit on the total size of these arguments. It's 4 kilobytes, and I've read somewhere that with recent GPUs it can go up to 32 kilobytes. So it's plenty. So the limitation of this is, of course, that you cannot pass large arrays of data by value, pass the pointers to the list of arguments. And then each thread, so when you run it, you will create lots of threads, and each thread will run exactly the same function. So there must be a way, when you are inside the function, to tell which thread is running it. So a certain number of variables are automatically predefined. They are a thread index, and there is this suffix .x, .y, or .z. So it means that the indexing system can be three-dimensional. It's useful if you want a natural mapping between the thread IDs and a volume space, for instance. It's used for that mostly. You have a block index, so this is an integer, and again it can be three-dimensional, that tells you the number of the block you're in. Block dim, again with 3 dimensions, it gives the sizes of the blocks in the 3 directions. And grid dim is the number of blocks, again in the X, Y, and Z direction. So, for instance, 2-dimensional indexing will be used if you want to map into the entries of a matrix. If you have a kernel with arguments, so this is a naive kernel that will add 2 matrices and put A and B and put the result in C. N is a constant that has been defined as well. It will be natural to call this kernel with 2-dimensional indices. So you have .x and .y with block ID, block dimension, and thread ID. In the x direction, you make an integer I. With the same in the y direction, you make an integer j. And then I and j are the 2 indices to access the 2 entries of the matrix. If your data is unidimensional, there is little interest in having 2-dimensional indices. It will just make your life easier. There are some size limits to the number of threads per block, the number of blocks you can have. The number of threads per block is limited to 1024, and this is a hardware limitation. The maximal number of blocks you can have in a given, or you can call a given kernel with, has also a limit, which is super large, so you usually don't have to worry about it. It's 2 billion. And this looks like a rather software-ish limit, because 2 to the 31 is probably the largest unsigned integer you can have in a single precision. And then there are also limits in the number of blocks you can have in the second and third directions. It's 65,000 something. There is a limit in the x direction, but I think it's much, much higher. And then something I said before, you can choose blocks which are smaller than 32 threads, but it's not very useful because it's a waste usually, because 32 is the smallest group of threads that the GPU will see. If you use less than 32, you're wasting some of this thread. So now you have defined the kernel. We have to learn about how to call it. So the call of a kernel is a little bit like calling a function in C. You put the name of the kernel, you have the arguments between a pair of parentheses here, and then you have these additional arguments which are between 3 times the inferior symbol and 3 times the greater symbol. And there can be up to 4 arguments in this section, and they are used to specify other parameters of the kernel code, which are the number of threads, the number of blocks, and a few other things. So I will explain what they are. The first argument is a number of blocks. It can be either integer, so this is where, in the case where you use only one dimension of indexing, so you just put an integer. Or you can use this type, which is a CUDA type, which is predefined in the CUDA library. It's called dim3, and it's it's a type that can hold up to a triplet of integers. Okay, but you don't need to specify all integers if you don't use the other dimensions. So, for instance, the syntax I used here will specify that you have 512 blocks in the x direction and only 1 and 1 in the y and z directions. So it will be like a single dimensional indexing for the blocks. You can put two numbers different from 1, and therefore it means you're using the x and y dimension. And if you put 3, then you're using a fully 3-dimensional indexing. The second argument here is the number of threads per blocks. Again, it can be either an integer or one of a variable of this type to specify in the 3 dimensions how many threads you have in a given block. So that gives you the size of a block in the 3 dimensions. The third and fourth argument are optional. So there are many instances where they are not used. The third argument specifies or provides a way of specifying the amount of shared memory that will be used per block, and it's in bytes. If it's not present, then it's assumed to be 0. So you're not going to use shared memory. And the fourth argument indicates the stream in which this kernel will be running. So this is used as a way of synchronizing or keeping unsynchronized and related tasks. So, for instance, if you allocate memory in a certain stream, and then you initialize this memory in the same stream, it's advised to run a kernel that will use this memory also in the same stream, so that it's not used before it has been initialized. So within a stream, things stay ordered in the order in which you submitted them to the stream. One remark: if you want to use the stream, so the last variable here, but you don't want to set shared memory, you have to put explicitly 0 for the shared memory, otherwise the program will get confused between the third and the fourth arguments. So that's the only caveat. So now, when you start a kernel, you have a certain number of threads, and it's a kind of hierarchy of threads. There is a bit of jargon on this slide. The set of all threads corresponding to a kernel is called a grid. The grid is divided into blocks whose size is defined the size and the number of the blocks is defined when you start the kernel. CUDA guarantees that all threads in a block run on the same stream multiprocessor, so the same chip, and they see the same shared memory. And in fact, that's the reason why they can be synchronized easily. One very important thing is that if you have several blocks of threads in the execution of your kernel, there is no guarantee that the blocks run simultaneously. There is also no guarantee that the block 0 will run before the block 1. Could be the other way around. That depends on what instructions they have to do. So you should not, as a programmer, when you code your kernel, assume that the blocks will be ordered in a particular way, for instance. This would lead to undefined results. There is a further subdivision of the blocks. In fact, the block is divided into groups of 32 threads, and this is called a warp in the CUDA definition. And this 32 corresponds to the set of threads that are almost forced to execute the same instruction at all times. This is mostly a hardware notion. It's really very much tied to the underlying hardware, but there are a few functions to do manipulations on these blocks of 32 threads. I will tell you about one of them later on. So the simplest way to set up a kernel, or the start of a kernel, is to have a block size which is a multiple of 32, because that will be an integer number of these groups of 32. And then the total number of threads should be, in general, an integer multiple of the size of a block. Okay. If it's not like that, then you will have to be careful towards the end of your arrays that you're not reading into places which are not allocated, or that you're processing completely the array until the end. If the length of the array you have to process is an integer multiple of the size of a block, then you're guaranteed that it will terminate gracefully. And you don't have to have this special test for the last block.
Question. You said that all the threads in the same block run on the same SM.
Mm-hmm.
But can you have many blocks on the same?
You can. Many, I'm not sure, but you can have several blocks running on the same chip. But it's not something you need, and it's not something you can control.
I may happen, but
it may happen, but it's decided by the hardware, depending on how large are your blocks. Because if you want to run a block with 1024 threads, it takes more cores than a block with only 64 threads. So the big blocks, perhaps you can only run one at the same time on one of these chips. Smaller blocks can share one of these chips. But it's not something you have to worry about. It's beyond what you can control in the software.
But you can control the size of the block.
You can decide the size of the block. So if your blocks, suppose you have you know that this chip for your GPU have 512 cores. Perhaps it's not a good idea to have 1024 threads in a block. It will work because the software allows that, but they will have to run in sequentially, so 512 and then 512, and then the software will maintain some state variables so that they can communicate anymore.
Conversely, if your blocks are 256, then maybe you may have two blocks. I don't know.
You could have two blocks if your kernel is calling more than one. What is also a waste of resource is to have only to run a kernel that uses only 256 threads, while you have many more computing cores available. So in general, the best or the recommended strategy is that you want to send lots of threads to the GPU, so many more than there are available cores. And this way, the GPU is always busy doing something. The other reason why you want to send many threads to the GPU is that the scheduler, so the part of the hardware that decides which thread to run now, which threads must wait, is looking at, well, the list of threads, and among the list of threads, those that have their arguments ready, so which means already transferred to the chip for doing some calculation on them. And for the others, it will request from the main memory, and this will take some time. So if you have only few threads waiting, and all these threads have not their data ready to do computation, then the GPU will have to wait, doing nothing. While if you have lots of threads queued on the GPU, the probability that no thread has its data available for doing computation is rather low. And that's a way of hiding the latency related to doing a round trip to global memory to fetch the data. While this, I told you last week that this can take of the order of 500 clock cycles, but during these 500 clock cycles, the GPU is just running other threads, not wasting its time. Okay. The last topic I want to discuss today is the notion of divergent code. So one thing I mentioned several times is that the threads run in blocks of 32. This is the smallest entity that will run on a GPU. And the GPU likes very much that these 32 threads are doing exactly the same thing. And divergent code is a program or a piece of code where this is not the case, where you have a test and the result of the test depends on which thread, can be very different according to the thread, and depending on the result of the test, you have to do a different calculation. So I made a little, I cooked a little example. I wrote only the important parts to illustrate my point. There are 8 functions, so this is F0, and then there are 7 more that I didn't write, F1 to F7. So these are functions that take 2 numbers and produce 1 number as a result. And they are chosen, it's just a silly example, but I will choose them so that they are different, but of similar complexity, so using the same number of instructions, but not the same function. And then there are 2 kernels. The first one is what I would call a non-divergent kernel. It takes 2 arrays and applies this function on every element of the arrays to replace the first array, and it's calling only the function f0. So it's this one is guaranteed that all the threads are doing exactly the same operations. And then the second one is what I will call the divergent kernel. So there is a switch to make a test. And the switch is taking the remainder of you take the thread number, you divide it by 8, and you look at the remainder. And depending on this, so the remainder is between 0 and 7. Depending on this remainder, you call the function f0, or you call the function f1. So it means that thread 0 is calling the function f0, thread 1 is calling f1. Thread 7 is calling F7, and then thread 8 is calling F0 again, and so on. So there are 8 possible cases, and therefore it means 8 logical branches of execution. And then I timed this little example on my laptop. So the two kernels are doing exactly the same number of arithmetic operations, but one is doing the same thing in all threads, and the second one is doing different things in different threads. And you see that the computing time has doubled when you have the divergent code, even though it's doing essentially the same number of instructions. So you could ask why didn't it get multiplied by 8 rather than just a factor of 2? And I don't have a precise answer to that, but I believe that it's because in the execution time of the kernel, the computation of this function is not the only thing that takes time. There is also the computation of the indices, for instance, the fetching the memory, and so on. So the computations in these functions themselves is only a fraction of the total time, and therefore if you have 8 divergent branches for this function, the compiler is nevertheless able to see some things that are common and can be done in parallel. But when the scheduler reaches a point where there is really a difference between the threads, different instructions in the two threads, it may decide that it runs this thread first and the second thread second, and therefore for this particular instruction, it costs twice more in terms of time. Well, there are places where the compiler is smart enough to disentangle that and remove the test. So for instance, if you have a test, but the test depends on constants which are defined in the code, and they are known when the code compiles, then the compiler will just remove the test, and that will be faster. Yes.
If you would switch so you had a switch of thread index, if you would switch that to switch of
Block index?
yes, would you expect the same regression?
No, because the threads of different blocks are automatically also in different warps, so they don't have to execute in lockstep. They don't care. Okay. It's only for this small entity of 32 threads that the scheduler likes them to do the same thing. Yeah, so this is a very good question, because it will make me say something I had forgotten to write, which is that the concept of divergent code is only applicable to these small entities, the warps, so blocks of 32 threads. You don't care whether one block is executing the same sequence of instructions as another block. This is irrelevant for the performance. Of course, if you have one block which is much slower than the others, it's how to say, the overall time will be determined by the slowest block, as usual. So, so sometimes the compiler is smart enough to see the outcome of the test at compilation time, so it will in general produce better code in this case. In some cases also, the compiler is able to rearrange the code to avoid the branches altogether. This is usually the case when the number of instructions in each branch is a small number of instructions, so the compiler can do some tricks. I believe in the example I had here, the functions are simple enough that the compiler will actually not produce function calls in the binary, but it will just copy the interior of the function directly in the place where it's called. It's called an inline function. And when it does that, it can more easily see the common patterns between different functions and simplify the code and make it faster. But if you have a big complicated function, the compiler will not try to inline it, and it will just be treated as some opaque thing that you have to. So anyway, a best practice is to think a little bit about this when you write the code of your kernel in order to avoid as much as possible branches in your code. Yes.
Yes, but wondering if your function has some kind of if statement that's becoming divergent in the same way, or?
Yes, it depends. So when I say that the compiler tries to remove the branches, let me get a piece of chalk. The compiler will do this. Suppose you have a test, you have some variable, and if the variable is less than 0, you calculate, I don't know, y equals x plus 2, and otherwise you have y equal the square root of x. Okay, so this will, if taken literally, this will be a branch, and therefore will code the code to diverge. But in fact, the compiler will translate this into something which is written like this. So in the C syntax, it will be like this, and then you do this, otherwise you do square root of x. And this is considered to be just a single instruction, and therefore it has no branch. It doesn't mean that the two sides will be calculated. This won't produce a mistake if x is, because x plus 2 will be evaluated, not the square root. But in the sequence of binary instruction, or if you want, this C statement is translates into a single instruction, and therefore you just run this particular instruction in all the threads, and it works without branching. Otherwise, for cases a little bit more complicated, what the scheduler will do is that it will run the two cases in full. So the first case will be run by the 32 threads. The second case will be run by the 32 threads also. The compiler does that when there are not many instructions inside this or this, and it's not costing a lot to just run the two instructions for all threads. And now, if between these braces you have 1,000 instructions and another 1,000 instructions in the second brace, the compiler will probably not do that because it would be too expensive. So my impression is that this is not something you can control. It's just the compiler looks at your code and decides what it thinks is best. Which may or may not be true. My personal take on this is that the people who wrote the compiler know a lot more than me, and therefore I kind of trust what's produced. But probably there are ways to write your code in a certain way to trick the compiler into doing this rather than that. If you know enough about the inner workings of the compiler. Okay, so this is the end of the second lecture. I can tell you what I will talk about next week. I will discuss in more details about streams and how to synchronize various activities on GPU. I will talk about shared memories. So I mentioned it several times, but I've never explained how you can access it and use it. And then I will talk about something which is very often done, which is called reductions. So reduction is when you have a large array, say with billions of entries, and you want to compute, for instance, the sum of all elements in the array. So if you have 1 billion entries on the array, the sequential version of this will have 1 billion minus 1 additions, and will take 1 billion minus 1. And so the idea is to try to perform this reduction by using the parallelism to its largest extent to reduce the number of and in green you have the program for the force.
Thank you, François. So some more questions. Also online, you may ask questions if you want.
You know, if there are some, if there is a profiling tool or something, so that you
Yes.
can count how many.
Yes, there is one. I've used it a couple of times. I forgot its name. It's part of the CUDA package when you install it.
So you have to combine with some special option, and then you analyze what's produced during execution. Is it the same as
I think you don't even need to compile the special option. The CUDA part of the code at least. And what it tells you is it shows you on the timeline of the execution of your program, and it shows you the time spent on executing kernels, memory transfers, and so on. You can also see if you manage to overlap them, for instance, to exploit more the parallelism. It can be useful for that. So it requires that you run your program for a minute, it records some data about the program, and then when you stop it, it shows you this display of the timeline events during this period. Okay.
This example code in the web page of the course?
Yeah, so I'm sorry, I was a little late in doing that. I have to clean up a little bit this code and add some comments in it so that it's more readable. And what we decided is that I will send them to Ricardo, and you will put them in the same place as the PDF file.
The examples, yes. And the slides, I will replace the file.
So the slides are also not finished for lecture 3 and 4. So the PDF file of last week will be replaced by that of this week, and progressively it gets more complete. Yes, so the examples, what I will try to do is to have a kind of folder with one subfolder for each example. In each subfolder, there will be the source code and the make file, so that you can compile it with just one command, and then you can run it. But these are simple programs, like 20 to 30 lines each, to illustrate one particular point of the course, not a complete process.
Do you know where we can find information for trying them on the IPhT? You mentioned in the beginning that they are 2 GPUs, right?
Yes. Well, if you have an account on IPhT network, you can already log in on this computer. You can ask this gentleman here. You don't need a special account for Akira. It's the same network password.
Same password as
With user machines. You log on this machine, and you can you copy a CUDA program you wrote elsewhere, for instance. You can compile it there and run it. I just had one glitch once, which is that the compiler didn't find one of the CUDA libraries, and I had to set the path myself by hand because it was installed in an unusual place. But except for that, it works very easily.
have permission to run your codes in the cloud, the GPU?
Yes, so the little programs are mine, and I don't mind if you use them anywhere. There is one example I took on NVIDIA's website, which I believe is open source because it's part of their documentation for explaining the concepts and so on. So there is nothing that is restricted.
François, I guess that when you mentioned the profiler is NVProf.
Yeah, perhaps. There are two profilers. One is something that you run in a terminal, and it outputs some numbers that tell you about various aspects of the running of your program. And there is a graphical one that shows in a nicer way some information about your program. I forgot how this one is called.
Okay. So maybe we can stop here if there are no more questions. And I think that online there are. Yeah. Okay. So thank you. Thank you.